Are you still playing badminton?
A little more tennis these days than badminton.
Okay,
Badminton days were from IIT Delhi days.
I see.
Do you play badminton?
No, it's yeah, not maybe backyard style.
Vijay?
No, not. I don't know. Not too much. Maybe.
You wanna try screen sharing actually, John, just to make sure that you have the right.
Sure. Send request.
Oh, great.
Do we start on the hour or at Berkeley time?
No. Well, somewhere in the middle. So usually 5 after 4. 3
Yeah.
4 minutes after that. So.
And let's see. Can you see that?
Yeah, looks great.
Yeah.
Hi, Robert.
Hello.
Hey, good to see you.
Good to see you too.
Howdy.
Hey, hi, Stephen. Hi, Robert.
Hello.
Hi, good to see you.
Good to see you too.
Likewise.
We can start in a couple of minutes. Let me just make sure. Okay. All right. So let's see. Shall we get started? So well, welcome everyone. This is it's a great pleasure for me to introduce our speaker today. John Wright is one of my favorite colleagues here in Berkeley. He got his PhD from CMU and spent time at MIT and Caltech and UT Austin before coming to Berkeley. So John's work has been on understanding quantum states, on quantum tomography through his PhD dissertation. He was involved in this really surprising paper about the power of MIP star, MIP star equal to RE. And this, this result that he's speaking about is I think, also extremely elegant, and really looking forward to the talk, John.
Thanks, Umesh. You're one of my favorite colleagues here too.
Thank you.
Yeah, so yeah, I guess I'd like to just tell you guys about this kind of fun project I worked on last year with Adam Booland and Tudor Djurgica Tiron. It's about this state hidden subgroup problem and an efficient algorithm for locating unentanglement. So let me begin this talk just with like a little puzzle, fun little puzzle for us to start with. So let's say we have a quantum state A, a pure state on some number of qubits, maybe 4. And then we have a quantum state B, a pure state on some number of qubits, maybe 4 as well. And if A and B are both in pure states, then if we draw this line down the middle, what we'll find is that there's no entanglement across this cut that goes, separates the left half of the qubits from the right half of the qubits. Now what I'm going to do is take these qubits and I'm just going to scramble them up, okay? And the whole state now, consisting of all 8 qubits, I'm going to call psi. And I'm going to define a couple of subsets. So S, I'm going to define to be the set of the blue vertices. So it's a subset of the numbers 1 through 8, size 4. And then T, it's going to be the complement of S. So it's going to be the set of all the purple vertices, also a subset of 1 through 8. And note that psi is unentangled across this ST cut. So in other words, it's a product state. We can write it psi is equal to, ket A on the S qubits, tensor with ket B on the T qubits. But now what I'm going to do is I'm going to delete the colors. Okay, so I've removed the labels on these qubits. And now I'm just going to give you the state psi, or n copies of the state psi. And your goal is to find S, or equivalently to find T. Okay. So this is what we call the hidden cut problem. I placed a cut in the state, I scrambled it up, and I've hidden it, so you don't know where it is. Can you find it? And one way you can solve this is just using full state tomography if you want. Psi, it's an n-qubit state, and so it's a 2 to the n dimensional state. But if I want to do full state tomography on psi to learn it, it's going to require exponentially many copies. And of course, the way that you would do this, of course, you do full state tomography, you learn the entire state, and then you can just check for every s, giving your learned version of psi, whether it's a product state over s. So it's not just inefficient computationally, it just requires too many samples of the state to work. So the question we'll be looking at today is it possible to do this with not exponentially many copies or polynomially many copies? And before I answer this question, what I'm going to begin with is the easier question of just suppose you already have a guess for what S and T are. How do you check that guess? How do you tell if psi is a product state across S and T already? So this is a well-known problem. It's been studied for a couple decades now, maybe more, called product testing. So let me just remind you how product testing works. So in product testing, your input is going to be some bipartite quantum state, psi AB, on 2 registers A and B. And your goal is to output the word product if indeed psi AB is a product state. So it can be written as A tensor B across the A and B registers. And then you want to output the word entangled if your state is epsilon far from product. And what do I mean by this? Well, epsilon far from product, it just means that the trace distance between your state psi and any product state V is at least epsilon, okay? So for any product state V, you're always at least epsilon far in trace distance from that state. That's what it means to be epsilon far from product. So pictorially, if this is a set of all states, the set of product states, they make like a tiny fraction of the set of all states. And then the set of epsilon of states that are epsilon far from product, maybe they're this red region over here. And then there's this kind of gray region that's an intermediate between these product states and epsilon far from product states. And these are the states that are, they're not product states, but they're not epsilon far from product either. And these are just very close to being product states. And they're just too close for me to reasonably ask you to detect that they're not product states. So I'm going to design this algorithm, and I'm just going to say for whatever algorithm you use, I don't care what it does on this gray region. All that matters is what happens in the green region and the red region. So this is just a standard property testing model. Now, here's a well-known fact that there is an algorithm that does very well in this problem called the swap test. The swap test has the following guarantees. If your state is indeed a product state, then the swap test will always output the word product. On the other hand, if your state is epsilon far from product, then the swap test is going to output the word entangled with probability at least epsilon squared over 2. Okay. So, it's not going to do it all the time, but with epsilon squared probability, it will correctly detect that you have an entangled state. And furthermore, the swap test is like very efficient. It uses 2 copies of the state. Okay. All right. And so, if a single application of the swap test correctly detects that it's entangled with probability epsilon squared, that means you only have to run the swap test 1 over epsilon squared times to detect that it's entangled with, let's say, 99% probability. And since every time you run the swap test, you consume 2 copies of the state, that means that to solve this product testing problem, you only need a big O of 1 over epsilon squared copies. Okay, and because it'll be useful for our later application, let me remind you actually, how does the swap test work? So to begin, it relies on this unitary matrix called the swap matrix. So given some integer d, the swap matrix, it's a unitary that acts on 2 registers of size d as follows. So if you give me ket I tensor ket j, and then I apply the unitary swap to it, it will output ket j tensor ket I. So we'll just swap the two registers. And by linearity, okay, so I defined it on a basis. And since I've defined it on a basis of the whole space, it extends to an action of the entire space via linearity. And it turns out you can check that if I apply the swap matrix to any product state, U tensor V, then it will always swap the two registers and give me V tensor U for any two product states, U and V. Okay, so let's suppose, we have a product state. What that means is that psi AB can be written as, A tensor B. So let's look what happens when we take two copies of this product state. So psi AB tensor psi A prime B prime. So A prime is, a copy of the A register, B prime is a copy of the B register. And now I'm going to apply the swap unitary to the A and A prime registers. Okay, so expanding our states, psi AB is A tensor B, psi A prime B prime is also A tensor B. And if I apply the swap matrix to the A and A prime registers, what it's going to take is this A on the A register and the A on the A prime register and swap them. And that will give me exactly the same thing back because, I have A on both registers. So this just returns my original state psi AB tensor psi A prime B prime. The swap wound up doing nothing. And therefore, if I apply swap to two copies of psi AB, what I get back is psi AB. But it's a fact, I'm not going to prove it here, but it's something that you can check. If psi AB is not a product state, but it's actually epsilon far from product, then this quantity right here is bounded away from 1. So psi AB tensor 2 times swap tensor or times psi AB tensor 2. That's at most 1 minus epsilon squared. And the way you should think of it is this is the state swap times psi AB tensor 2. That's what happens if I take the two copies of psi and apply swap to them. And now you can ask, did I get back my original state, psi tensor 2? And if not, what is the overlap with my original state? And what this tells us is that the overlap is not just not equal to 1, it's bounded away from 1 by a quantity epsilon squared. Okay, so in summary, if psi is a product state, then applying swap to it, to two copies of it does nothing. But if it's epsilon far from product, then applying swap to it will give you a new state that's actually noticeably far from what you started with. And the swap test, it just uses two copies of psi AB to check this. It wants to check, does applying swap to my two copies giving back the two copies, or does it change them? And like I said, if psi AB is a product state, then the check always passes and it always outputs the word product. But if it's epsilon far from product, then the check will fail with probability epsilon squared over 2, in which case it will output the word entangled. So that's how the swap test works. All right, so let's get to our hidden cut problem. So that was the case when, if I had a guess for where the cut was, I could use the swap test to verify it. But yeah, remember our hidden cut problem. So let me define it formally. We're given an n-qubit quantum state psi as input, and it has the promise that it has a unique hidden cut s comma t. So pictorially, it looks like this. You have some qubits, some of them are purple, some of them are blue, and it's a product state across the blue and purple qubits. And what do I mean by unique? Well, there are two ways of formalizing what it means to have a unique hidden cut, and they turn out to be equivalent. So one way you could formalize it is say, well, yes, my state psi is a product state across S and T, but within S and T, both A and B are epsilon far from being product states themselves across any cut. Okay, so there's one cut where I do have a product state, but then within going further within the two sets, you're very far from product. And equivalently, this is identical to just saying that for any other S prime T prime cut, which is different than ST, psi is epsilon far from product across that cut. And so that's the input. You have a quantum state with a unique hidden cut, and your output is just going to be the subsets S or T. Now, I think, yeah, our paper, I think, is the first one that that studies this specific problem, but a very closely related problem was previously studied in this very cool work of Harrow, Lin, and Montanaro from 2016. So they studied not the search version of the problem, but the decision version of the problem. Okay, so what does the decision version mean? The decision version is you're given, copies of the state psi, and you just want to detect whether there exists a hidden cut in psi or not. You don't necessarily need to find the hidden cut. You just want to know, is there a hidden cut, or am I far from being product across every cut? So they gave an algorithm for this problem. It uses n over epsilon squared copies. And it distinguishes the following two cases. So in the yes case is when psi has a hidden cut across some S and T. And the no case is what they call genuine multipartite entanglement. And what this means is that your state psi is epsilon far from product across any ST cut. Okay. So again, their algorithm was just detecting whether there exists a hidden cut or not. And one reason they were just interested in this problem is, suppose you go in your quantum computer and you want to generate an entangled state, like a highly entangled state. And what you'd really like is for your highly entangled state to be entangled like any which way you slice it. So it'd be kind of disappointing if you if you tried to make a very entangled state, and then I just came along and pointed out to you that actually, qubit 10 is unentangled with everything else. So this was an algorithm that they designed to hopefully detect whether you're successful in doing this. And there was a follow-up work just last year, actually, by the same Montanaro and Jones, and they gave a nearly matching lower bound for this problem. So they showed that in the case when epsilon is a small constant, then for this decision version of the problem, n over log n copies are required. Okay. So this almost matches up to this log n factor, the upper bound that they showed. Now, one thing is that their algorithm was computationally inefficient. But what I'll at least be able to do is show you a very similar algorithm that we gave not for the decision version of this problem, but the search version of this problem, which was inspired by their algorithm. So yeah, inspired by their algorithm, let me first tell you like an inefficient algorithm for the hidden cut problem, the search version of our problem. Okay, so we already saw how to test if your state psi is a product state across some cut ST using the swap test. So a natural thing to do is, well, why not run this test using one cut S1T1, and then try it again for S2T2, then try it again for S3T3, and then so on, until you've tried all the cuts. Okay, so let me formalize how you would do this. And actually, first, let me look again at just a single ST cut. So what we're going to do is we're going to, instead of just taking two copies of psi to test if you're a product across the ST cut, we're going to take two T copies of psi. And if we do that, we can group our copies into pairs, into T pairs. And we can independently just run the swap test on all T pairs. Okay, so, if ST is indeed the hidden cut, then every swap test is guaranteed to output the word product. And so you'll just get, T products. So you're pretty confident this is just product across this cut. But if ST is not the hidden cut, then each swap test is going to output product with probability at most 1 minus epsilon squared. Okay. And so, if just a single one of these does not output product, then you're not looking at the right cut, right? So let's just bound the probability that they all incorrectly output product. So the probability that all the swap tests incorrectly output the word product in this case is at most 1 minus epsilon squared to the t. And so now I can make this probability very small. So for example, if I set t to be like n over epsilon squared, then, this like 1 over epsilon squared will kind of cancel with that 1 over epsilon squared, turn it into 1 over e, and then it's like you have a, e to the n or something like that. So if you set t to be n over epsilon squared, then your probability of detecting that it's of incorrectly outputting product is extremely small, like exponentially small n. So let me just define pi st to be the projector onto the all products outcome. So this is a projector that you get when you run all the swap tests and they all output the word product. And I'm going to write pi bar st for the complement, which is when at least one of them outputs entangled. And what this whole discussion tells us is that if we look at the trace of pi st times our 2t copies of psi, so that's the probability if we run this measurement on our copies of psi that it outputs the word product. This will get this trace is equal to 1 if st is a hidden cut. And it's going to be at most exponentially small in n if st is not the hidden cut. Okay, so here's the inefficient algorithm. Your input is going to be these 2t equals n over epsilon squared copies of psi. And you're just going to do the following. For all non-trivial cuts, st, you're going to loop over them all, and then you're going to measure your copies of psi with pi st and pi bar st. And if on any of these you ever observe the pi st outcome rather than the pi bar outcome, then you just halt and output s as your guess for the hidden cut. Okay, and let me just give you a proof of correctness. Each measurement, it will be correct. If you perform the measurement, it's correct whenever you're actually a product state across the st cut. If you're not a product state across the st cut, the measurement will err with exponentially small probability. So we'll error with probability big O 1 over 2 to the n. And there are at most 2 to the n cuts to look at. So you're only performing 2 to the n total measurements. And so if we want, we can just make this big O of 1 over 2 to the n small enough so that when we union bound over all 2 to the n measurements that we perform, the error probability is some very small constant, say 0.01. Now, if you haven't seen things like this before, you may say, but wait, doesn't each measurement disturb the state? Can I actually analyze this with a union bound, just like a naive union bound? But turns out the answer is yes. The analysis still works because there is a union bound that works in the quantum setting called Gauss quantum union bound, which is fairly standard if you're doing learning theory. And that completes a proof of that. Okay, so that shows that for the hidden cut problem, you can find the cut, not just detect whether one exists, but actually find it with n over epsilon squared copies of the state. Okay, but and like I said, this is very similar to the Harrow, Lin, and Montanaro algorithm for the decision version of this problem. So how did their algorithm differ? Rather than so they did, they took all these measurements, one for every cut. And rather than combining them with the quantum union bound, they combined them using something else known as the quantum Bohr bound. Okay, but notice this part of the algorithm, we have to loop over all exponentially many cuts. So even forget like implementing this measurement or whatever, just doing this loop is going to take you an exponential runtime. So what we want to figure out is, is there a way of doing this faster in polynomial time? So this problem, intrinsically, it kind of seems like it should require exponential runtime. I mean, how else do you search over all the subsets? And this suggests the possibility that you might have like an information computation gap. So like a natural problem where it's information theoretically easy, but computationally hard. Why would you want that? Maybe it's useful for cryptography, maybe. I mean, crypto, I guess people like to have problems which are information theoretically easy, but computationally hard. There's one application that has been suggested for this problem by, I guess, various people in quantum cryptography known as pseudorandom state length expansion. So this is just like if I have two pseudorandom states, A and B, is there some way of combining them to get a longer state that remains pseudorandom? And this suggests like one possible way of doing this, right? Just take A and B, scramble up their qubits to give you the state psi. And psi, it's a product across the cut ST. But if you don't know what this cut ST is, then maybe the state still looks pseudorandom to you. But of course, one way to show that this doesn't work is just if you can find an efficient algorithm for actually identifying the cut ST, then this has no hope of working just because, a truly random state will not be product across any cut. I will say my understanding is that this is, still a problem where it's not clear whether there are like true applications, even if you could design a pseudorandom state length expander. Maybe someone will correct me if I'm wrong, but yeah, my understanding is that it's still like a primitive people are trying to understand and construct it, but I think there are no like concrete known applications if you were to get some sort of pseudorandom state expander. Me personally, I'm like a info theory person. I like learning. And for me, it's just like a very natural quantum information theoretic problem. It's just, kind of a fun problem to design algorithms for. Okay, so what was the main result of our paper? We showed that there is, in fact, an efficient algorithm that solves this hidden cut problem that uses n over epsilon squared copies and runs efficiently. So polynomial in n and 1 over epsilon squared. And our algorithm, it was inspired by the hidden subgroup problem from quantum algorithms. And along the way, we define a state analog of this hidden subgroup problem that we call state HSP that people might find independently interesting. So let me tell you the key idea of our problem. So I'll tell you about our algorithm first and then tell you about the state HSP later. So the key idea, let's take two states, psi, two copies of psi on top of each other. And then I'm going to define a string x. For every pair of qubits, like vertical pair of qubits, I'm going to assign them a bit. So maybe the first pair gets a bit 0, second pair gets a bit 1, and so on. And if psi has n qubits, then this defines a length n string x, which is in 0, 1 to the n. And given this string x, I'm going to associate to it a swap matrix that I call swap sub x. And the way I define this is that, just whenever I have a pair of qubits that is 0, I'm just going to write down the identity there. And whenever I have a pair of qubits that have a 1, I'm going to write down the swap matrix there. I'm going to get identity, tensor swap, tensor identity, tensor identity, tensor swap, tensor identity. And swap of x, this will give you a matrix that is, an n-fold tensor product of things that are in I, comma, swap. All right, so let me write down some properties of this swap x. So first, let's let s, comma, t be the hidden cut. Okay. Then I claim that actually this swap sub x matrix, if you multiply by 2 copies of psi, you'll get back 2 copies of psi for a few nice settings of x. Okay, and what are those? Well, definitely this swap thing, it will do nothing if x is just all zeros, because in that case, swap of x is just the identity matrix. But more interestingly, if x is the indicator vector for the subset S, then what that will do is we'll swap all the qubits that are in S, but the qubits outside of S will remain unswapped. And so, we've already seen that if S is a hidden cut and I swap across S, across the 2 copies, then it preserves the state. The same thing happens for the indicator vector of T. So if I swap across T, I preserve my 2 copies of the state. And then finally, this actually also works when X is equal to the indicator of S plus the indicator of T. And why is that? Well, S and T, they're disjoint complementary subsets. And so their sum is actually just the all ones vector. And so that's what you get when you just swap everything in the first psi with everything in the second psi. It just gives you back psi tensor psi. Okay, in other words, swap will preserve your state whenever the string X is in the set H, where H is the set that contains 0 to the n, the indicator of S, the indicator of T, and 1 to the n. And what's nice about this H is that it's a subgroup of Z2 to the n. Okay, it's a subgroup that is generated by the indicator for S and the indicator for T. Okay, so that's fun fact number 1. And for any X which is not an H, well, that X will indicate some subset, S prime. You're not a product state across that subset. And so we saw before that if you're not product state across one of the subsets, S prime, if you perform a swap on that subset, it will map psi, 2 copies of psi, to something that's far from 2 copies of psi. And how far? Well, we saw the overlap would be at most 1 minus epsilon squared. So if you're in H, you preserve psi tensor 2. If you're outside of H, you perturb psi tensor 2. And the last thing is that these swap matrices, they have this nice property that swap of X times swap of Y is actually equal to swap of X plus Y. And this is just because, if I take swap and I square it, I get back the identity matrix. Of course, this is X plus Y. Everything is done modulo 2. And one way you can view this is just saying that these matrices are actually a representation of Z2 to the n, if you like representation theory. And I guess, when we saw this property, it really reminded us of a related problem that was studied, in quantum algorithms known as Simon's problem. So let me remind you what Simon's problem looks like. There you're given oracle access to a function f, which takes as input n-bit strings and maps you into some output set. It doesn't really matter what it is. You can imagine it's, colors, red, green, blue, and so on. And this function, it hides a secret string s. And what does it mean for the function to hide a secret string s? Well, if I take my function and I shift it over by s, it doesn't do anything. So for any x, f of x is equal to f of x plus s. But for any shift that I do, z, which is not equal to s, then f of x will not be equal to f of x plus z. Okay. That kind of felt to us like our problem, right? Like you apply swap for something in your set H, it will preserve your state, but anything outside of H will give you a different state back. And in Simon's problem, your goal is to find S. In our problem, our goal is to find H. So it seems similar. Oh yeah, so let me just say it. We have an object, that's F. It is invariant when shifted by an element of this hidden subgroup H. In this case, the hidden subgroup is 0 to the n and S. It gets completely changed when shifted by any other string Z. And our goal is to identify H. And yeah, this felt similar to the hidden cut problem. And let me remind you, how do you solve Simon's problem? Well, in step 1, you prepare the uniform superposition, sum over all x of ket x. Then you query f on this superposition, giving you, sum over x, ket x, f of x. You Fourier transform the first register and you measure. And what that will give you is a uniformly random string y, which is in H perp. So it's in, the set of strings that have 0 dot product with everything in H. And you can repeat this measurement over and over again until you have identified H. So eventually, if you collect enough strings to identify H perp, that will help you identify H. Okay, so given this algorithm as our motivation, this gave us an algorithm for the hidden cut, or suggested one. So, we're given copies of state psi. We want to find this hidden subgroup H, which is generated by the indicators of the subsets S and T. And we're going to do something very similar. We're going to prepare the state, which is the uniform superposition over X. And then we're going to tensor onto it the two copies of psi. And condition on X, what we're going to do is apply the swap sub X onto the two copies of psi. And then we're going to Fourier transform the first register and measure it. And it turns out that just like in the Simon's problem, this will actually give you a string Y that is in H-perp. So in the set of strings that are orthogonal to your starting H. And again, you can just repeat this until H has been identified. Okay, so that's basically the algorithm. Now, there's one like annoying problem with this, which is that unlike in the case of Simon's algorithm, the Y that you get is probably, aka definitely, not a uniformly random element of H-perp. So for example, if it wants, it could always return just the 0 string. That's an element of H-perp. And this has something to do with the fact that our guarantee is that, for an X that's not in our hidden subgroup H, the overlap between, the state after you apply swap and the original state, it's not 0. It just bounded away from 1. In Simon's problem, like if I shift you by the wrong thing, then I completely change the value of the function. Here, if I shift you by swap, I just slightly change what the state is. So yeah, this thing is non-zero. That can create a headache. But it turns out you can just amplify this gap and make this closer and closer to 0 by using more copies of the state. And just believe me, everything does indeed work out. Okay, and to just give you a little bit of intuition on how this works, I did just want to show you why do you actually get a Y that's in H-perp? Why don't you ever get something that's outside of H-perp? So this is just going to be, a calculation that's very similar to if you've ever done Simon's algorithm. It's very simple, very similar to that. So let me just do that. Okay, so we take our state here, and let's just imagine what happens when we Fourier transform that first register. Okay, so it used to be ket x. Now it's the superposition over y minus 1 to the x dot y of ket y. So let me pull the sum out of y on the outside. The sum of y, ket y, tensor with superposition over x minus 1 to the x dot y times swap of x times psi tensor 2. And what we care about, if we want to know what is the probability of measuring a y, we care about this vector right here. And what I want to show is that if y is not in H-perp, then this vector is 0. Okay, and that means that you'll never measure that y. Okay, so suppose that y is not in H-perp. Then what does that mean? That means, so you're in H-perp if your dot product is 0 with everything in H. So if you're not in H-perp, then there exists some string lowercase h for which your dot product is equal to 1 mod 2. So let's just take that string h. So this coefficient vector on y, we can calculate it the following way. So the star, it's equal to sum over x of that thing. So that's just copying that over. But now what I'm going to do is I'm going to take 1/2 of that, and I'm going to add to it 1/2 of this expression. So I'm averaging over x of minus 1 to the x plus h times y times swap of x plus h times psi tensor 2. So this is actually the exact same sum as the first one, except wherever I used to have x, I now have x plus h. But that's an okay thing to do because, as x varies over all 0, 1 to the n, x plus h also varies over all 0, 1 to the n. And now let's just look at two things here. So let's look at this first. This is minus 1 to the x plus h dot y, which is equal to minus 1 to the x dot y plus h dot y. And now h dot y is equal to 1, right? So that part is just going to be a minus 1. And so this whole thing is equal to minus 1 to the x dot y. Okay, so we get a minus 1 to the x dot y there, and then we pick up a minus sign here. And now on this swap, Well, what is this? This is swap of x plus h times psi tensor 2. As I said, this is like a representation, so this is just equal to swap of x times swap of h. And swap of h times psi tensor 2, that's just psi tensor 2, because h is an element of our hidden subgroup. So that gives us swap of x times psi tensor 2. And now we have one expression minus the exact same expression, and so the whole thing is equal to 0. And that at least completes a proof that you always get a y that's an h perp. You never get a y outside of h perp. And then the proof that like y has a decent enough distribution that you can actually make use of it. It's not too much more complicated. Okay, so Simon's problem, it's a special case of the hidden subgroup problem over z2 to the n. As we all know, there are other hidden subgroup problems that can be defined over more general groups G, and this has applications to all sorts of areas like factoring, lattice-based crypto, graph isomorphism, et cetera, et cetera. So our hidden cut problem, it can be viewed as a state version of the hidden subgroup problem over z2 to the n. And in our paper, we defined a more general state HSP over arbitrary groups G. Let me tell you oh yeah, and we show that certain algorithms for the standard HSP over group G wind up behaving similarly when you try to use them for the state version of the hidden subgroup problem. So let me define for you the state hidden subgroup problem. It's defined over a general group G, and so let G be a group and let R be a representation of G. So what does that mean? It's just a map that associates with every group element a unitary matrix. And it also obeys the multiplication relations of the group. And what you're given is copies of a quantum state psi, which hides a subgroup H. So H is the subgroup of G, and this quantum state hides that subgroup. And how does it do that? Well, for every element of your subgroup, lowercase h, if I take psi and I multiply it by the corresponding unitary, I get back psi. So it leaves psi unchanged. But for any h which is outside of your subgroup, if I take psi and multiply it by r of h, it gives me a new vector whose overlap with the starting psi is at most 1 minus epsilon. And now your goal is to find h using as few copies of psi as possible. So again, the hidden state problem is a special case of this when G is z2 to the n. The representation of G that you're using is just these swap matrices. And the states that you're looking at are of the form, psi tensor 2. The quantum state version, so this is like a quantum state version, like I said, of the standard HSP problem. We kind of like this because, people are studying a lot of quantum input problems now. So there's like a big complexity theory of problems that are inherently quantum. And this is, I guess, one more example of a problem like this that you could consider. This number right here, like I said earlier, it's really nice if that's 0, because you wind up looking a lot like the standard HSP. But of course, it's not always going to be equal to 0. It'll just be 1 minus epsilon. And we call this parameter epsilon the orthogonality allowance. So when epsilon is small, it makes your life harder. When epsilon is big, it makes your life easier. And like I said, it looks more like the standard HSP, turns out, as the orthogonality allowance epsilon tends to 1. I'll say a little bit more about why later. And it does turn out that if you're kind of bummed that someone gives you an instance of this problem and the orthogonality allowance is very close to 1, you can actually inflate this parameter epsilon and make it bigger and bigger in kind of a standardish way. And it's just like take your state and your representation and tensor them. So replace the representation of your group by the representation tensor k, and replace your states by the states tensor k. And if you get that, then your overlap, if you now tensor everything k times, it used to be 1 minus epsilon, now it's 1 minus epsilon to the k. And if you pick k to be, at least 1 over epsilon, then you can make this a constant. If you pick k to be much bigger than 1 over epsilon, you can make this very small. That's kind of what's going on, or one thing that's going on in our algorithm when we amplify things. And indeed, some facts do just transfer over directly from the normal hidden subgroup problem. So, if I have a hidden subgroup problem over a group G, and I now look at the state version of the HSP, it turns out if I have a hidden subgroup problem, a Fourier sampling algorithm that works for the normal HSP, then it transfers over pretty directly to the state HSP setting. And actually, that's basically all our algorithm is. It's this normal HSP, Fourier sampling algorithm transferred over to the state HSP setting. So the hidden cut algorithm is just the case of z to the n Fourier sampling. Turns out, just like in, I think that's supposed to be log of g, not size of g. Just like with the normal HSP, there's an information theoretic algorithm that works with, log g copies of your state. There's also a similar one that works for the state HSP. And the HSP problems for the normal ones, which seem computationally difficult, they still seem computationally difficult in the state version. And so it's a bummer if you're a fan of the symmetric group. Also doesn't seem to work here. Actually, let me say a little bit about this symmetric group. Why you might think you would like to solve it or use it for our problem. So let's say you take our state psi, as a cut S and a cut across T. And now let's imagine instead of looking at 2 copies of psi at a time, you looked at T copies of psi at a time. Well, if I took all of these columns and I permuted them by the same permutation, pi, and I took all of these columns and I permuted them by the same permutation, let's say sigma, then I would still get back the same state. So actually, like if I have T copies, my states are invariant under these larger permutations. So one thing you could imagine is, let me try to do the state HSP over the group G, which is defined across these, you specify a permutation for every column. Maybe you do a different permutation across each column, and that's your group G. So that's just ST direct product with itself n times, or direct sum, or Cartesian product. And in that case, psi tensor T will hide the subgroup of G specified by H, where H is just all of the permutations which are the same on S and then the same on T. So you specify a pi on S and a sigma on T. Okay, so then you could try to do one thing, which is just, set T large and then do Fourier sampling over this group G. Which is like the symmetric group times, n times. But we wind up showing this is like a bad idea. This is hard just for the same reason that like the symmetric group HSP normally is hard. And like Fourier sampling there fails, it's known. Fourier sampling here fails. So somehow it's like a bad idea actually to consider like T copies of the state at once. It's much better just to do 2 copies of the state. Okay, so, ours, we define the state HSP. Let me say, you can find analogs of state HSP or things that basically are previously in the literature, although we're the first, I think, to define the problem generally. But let me tell you a little bit about these. First, the standard hidden subgroup problem is indeed just, if you view it in the right way, an instance of state HSP. So why is that? So in the standard HSP, you're given a group G and a function that maps G into a set of outputs. So consider a function f that hides a subgroup H. What does that mean? Well, for every G and for anything in your subgroup H, then f of G is equal to f of G times H. And then for all G and all H which are not in your subgroup, f of G is not equal to f of G times H. So that's the standard HSP problem. Your goal is to identify H. And, the standard HSP approach typically begins just by preparing the state psi, which is like a uniform superposition over group elements G. tensored with f evaluated on G. But I claim once you do that, then you basically have an instance of the state HSP problem. Okay, why is that? Well, let R be what is known as the Wright regular representation of your group G. It's the thing that if I take ket G and I multiply it by group element H, then it outputs the vector G H inverse. So let's look at what happens if I take my state psi and I multiply it by this Wright regular representation. So it's going to take sum over G. And now in the first register, I'll have G H inverse times f of G. So let's do a change of variables. I'm going to call this G prime, in which case G is going to be equal to G prime times H. So this is just equal to the superposition over ket G prime tensor f of G prime H. Now, if we look here, if H is in your subgroup, then by definition, it doesn't change the value of this function at all. And so if H is in your subgroup, then G prime, sorry, this shouldn't say G prime. This should say this is equal to f of G prime. And if H is not in your subgroup, then this is not equal to f of G prime. And what that means is that if H is in your subgroup, then you get back ket psi. This is just, f of G prime. That's exactly what you have here. And if H is not in your subgroup, then every register here, the f of G prime H, is going to be different than f of G prime. And so what you're going to wind up with is a state that's completely orthogonal to your starting ket psi. So what does that mean? It's like the standard HSP in this version is just equal to the state HSP over the group in the case when the orthogonality allowance is 1. So whenever I multiply something outside of my subgroup, I just get a perpendicular state. Okay, so that's the standard HSP. There was another paper from 2017 by Lockhart and Gonzalez-Guillen that studied a state isomorphism problem, and you can put this in the state HSP framework very naturally. And in this problem, you're just given n copies of an n-qubit state psi, or sorry, you're given copies of an n-qubit state psi, and also copies of a state psi, the same state psi, but with a permutation applied to it. And now your goal is to find pi. So that can be viewed as an example of a state HSP problem. Then maybe the most natural and kind of commonly studied example of a state HSP problem that has already exists in the literature is the case of stabilizer states. So maybe let G be the group of n-qubit polys. And a stabilizer state is just a state psi such that if I take a poly matrix P and I multiply it by psi, I always get back psi. So long as P is in a set H. And what is H? Well, it's just a subgroup of G that psi is 2 to the n, and it only consists of commuting polys. And this is, a problem that's been studied a lot with stabilizer states. You're given copies of state psi, and you'd like to test if psi is a stabilizer state. So it's a testing version, or maybe you want to learn which stabilizer state it is, in which case you want to learn the hidden subgroup H. There's been a lot of work on this problem, and the testing problem is solved via an algorithm known as Bell difference sampling. And we actually contacted about a month ago by Hinch, Ioannou, and Crosco, and they actually showed that by using ideas from the stabilizer state literature, they can simplify our analysis and make it so that we only need to measure 2 copies of psi at a time. And actually, there's kind of a way of viewing our algorithm and Bell difference sampling, I think, as somehow similar algorithms. Okay, sorry, I know I'm running over, but I do want to give one more puzzle for you guys that I personally find interesting. So hopefully you'll indulge me. Just give me a little bit more time. Let's say same setup as before. We start off with some qubits that are blue, some qubits that are purple. And now, rather than them being in a product state, all I'm going to tell you is that across this cut, my state has Schmidt rank at most 2. So it's not a product state, but it's, very unentangled across this cut. And now, as before, I scramble up these qubits, call this whole state psi. Again, we can define S to be the blue vertices, T to be the purple vertices. And here's a question. Can you find S and T? Again, it's no longer product across this cut, but it's still very low entanglement across this cut. Okay, so just as before, the easier question is, suppose you have a guess for what S and T is. Can you identify S and T, or can you test this guess? In other words, how do you tell if psi is rank 2 across some cut S and T? So let me just briefly tell you about that first. This is a problem known as rank testing. Your input is a bipartite quantum state psi on 2 registers A and B. And what you'd like to output is rank R if psi AB has Schmidt rank across this cut at most R. And you'd like to say not rank R if psi is like epsilon far from any state that has Schmidt rank at most R. Just like the swap test, there's an algorithm that's known to work from past work of Ryan O'Donnell and myself that we called the rank tester. It has the following guarantees. If your state is indeed one of these rank R states across that cut, then the rank tester will always output the phrase rank R. And if the state is epsilon far from rank R, then the rank tester will output not rank R with probability at least 99%. And furthermore, the rank tester will use maybe a small number of copies, R squared over epsilon squared copies of psi. In our case, we just care if you're rank 2. So that's 2 squared over epsilon squared, aka big O of 1 over epsilon squared. Turns out this rank tester is like a natural generalization of the swap test. I'll tell you how it works. You take your state psi AB, you trace out all the B registers. So that gives you a mixed state on A. Let's say you have T copies of that mixed state. And now you measure them with an algorithm known as weak Schur sampling. If you don't know what it is, no worries. You receive a Young diagram lambda, and then you output rank R if lambda has at most R rows. And otherwise, you output not rank R. So that's that algorithm. Okay, so how can we apply this for this hidden rank 2 cut problem? Well, again, if we do the same analysis like we did with the swap test, if you take this rank tester and combine it with Gauss quantum union bound, it shows that you can indeed find a hidden rank 2 cut with n over epsilon squared copies of psi, but inefficiently. Okay, so the question is, can we do this efficiently? And let me tell you one idea motivated by our tester. Let's say you take psi, you take T copies of psi, where T is the number of copies that you need for the rank tester. And then similarly, you do a similar thing, right? You write X to specify a subset of these columns. So that's a string of length n. And what I'm going to do is let capital X be the subset of n that's indicated by little x. And let's imagine that we went to these these registers, the X registers, and we did the rank tester on psi on the X registers, and let pi sub x and pi bar x be the measurement that you perform there. So what this would say is, if it is indeed the correct cut, so if x is the indicator for the ST cut, then pi of x times psi tensor t is equal to psi tensor t. And okay, these are projectors. What we need to define are unitaries. So I'll turn this into a unitary by setting r of x equal to pi of x minus pi bar. And here's a sad fact. R of x times r of y is not equal to r of x plus y. So if you do this kind of natural way of trying to generalize our hidden cut tester, what you find is that the matrices you write down, they don't give you a representation of your group. And because these do not form a representation, we can't use the state HSP framework. So we don't know how to solve this problem. I mean, it's information theoretically easy, could be computationally easy, or it could be computationally hard. I don't know the answer, but I'd be interested to find out either way. All right, let me conclude with some final questions. Now we have this hidden cut problem. I like it. I think it's a fun problem. Are there applications of it? Is it useful in the real world? Are there more applications of this HSP framework to state problems? There's this lower bound of Montanaro and Jones. They got n log n. Can it be improved to n over epsilon squared, matching these upper bounds? And finally, my favorite question with entanglement testing, this one's been open for like about 10 years now. If you have a pure state, testing if it's entangled is easy. Use a swap test. How many copies do you need to test if a mixed state is entangled? We still don't know the answer. Even simpler, how many copies do you need to test if a mixed state is PPT? I also don't know the answer to that. All right, I'm all done. Thanks.
Great, thank you. Thanks, John. That was great. Are there any questions? Yeah, Venkat, do you want to? Do you just want to go ahead and ask the question, Venkat?
Yeah, I just managed to unmute myself. Sorry. Can you hear me?
Yes.
Okay. Thanks for a lovely talk, John. I just had an abstract question, not motivated by any applications, but seems to me that all the groups you're dealing with are discrete, and it struck me that there might be versions of this or continuous groups, which in your notation would correspond to epsilon maybe being going to 0 rather than 1. So you start to see some distance as you move away from the subgroup, but you don't have a jump in the distance, so to speak. I mean, is that something that your techniques can handle?
That's a good question. I don't know. I mean, there are definitely infinite groups that people care about, that people study a lot in terms of quantum. So like the unitary group is one. And I can definitely think of states that, like state problems that are, for which there's like a subgroup of the unitaries that leave your state invariant. For example, if your state is just like a projector onto some subspace of, let's say, rank R, then your state is like invariant under any unitary that acts within that subspace. And that's like a kind of a subgroup of the unitaries. People also like doing various types of Fourier transforms over unitaries as well. So I would imagine that like these sorts of techniques and maybe this way of looking at it could be useful for those sorts of things. But yeah, as you say, like with infinite groups, like you can be outside of the subgroup, but also be very close to the subgroup as well. So you'd have to like make sure the definition accounts for that, I guess.
Yeah, I was thinking more like along the lines of how would your asymptotics and the complexity sort of depend on your parameter epsilon, right? If the epsilon didn't exist, you might start to see more interesting complexity kinds of estimates. But it's interesting to know the question's interesting anyway. Thanks. Yeah. Okay.
Thanks.
Marius also asked a question whether it's essential that R of G leaves the state completely invariant, or whether you can also allow for a global phase.
Probably a global phase is fine. What do you think, Adam? Global phase?
That's a good question. I'm not sure immediately off the top of my head. Because like one way of thinking about the algorithm is like, you're kind of like preparing a coset state on the first register, like by applying your controlled group action on the second register. Like if your group action were completely orthogonalizing, then if you could show that because it's a representation, each coset maps to a different state on the second register, so that's orthogonal. So then tracing out the second register prepares a classical convex mixture of random coset states on the first register. And I would worry that if you apply global phases, they become relative phases in the controlled group action. So that might give you a coset state with some with some like relative phases between it. That
the other
that
thing
that
is,
would be my concern off the top of my head, but I don't know, we'd have to look at the calculation a little more carefully.
I feel the other thing is like, well, if you're invariant under a subgroup, subgroup's always going to contain the identity. Your representation of the identity is always just going to be an identity matrix. So the identity representation can't give you a global phase. So that would definitely mean, I think, sometimes your phases are going to be different.
Marius, did you want to follow up?
Thanks.
Okay, thanks. Okay, we have one more question. Whether there's also no known efficient algorithms for testing matrix product states, given the, rank.
Oh, yeah. I guess it's like it depends if you are, sorry, is this matrix product state if I know the ordering of the qubits? Or if someone takes the matrix product state and then scrambles the qubits up and gives me that? Is that the question?
I guess the question doesn't specify it, but maybe we fix the ordering.
Well, if I fix the ordering, then yes, I can do it.
Right.
If pardon?
But if you don't fix the ordering, then maybe not.
Yeah, I mean, I think I can even efficiently learn matrix product states.
Right.
With efficiently. You can test them even more efficiently if you want, but you can definitely learn them efficiently. But yeah, if you don't fix the ordering, I don't know. Yeah, no idea.
Okay, if there are no more questions, shall we move to the panel?
I have one brief question. So, right, you mentioned this analogy to Bell difference sampling and the state hidden subgroup problem. So I was wondering if your higher rank question is related to learning stabilizer states with a few T gates, or if you can relate it to that.
Good question. I don't know.
Okay, because that we know that we can do it efficiently if you just have a few T gates.
I think you can. I think this is something we learned actually after QIP based on some discussions with many folks. Is that I think you can use state HSP framework over the poly group to show that you can learn if a state has some has a small number of stabilizers or not, right? So in the case that you have a stabilizer state, you throw a few T gates in.
I guess I'm wondering if you can sort of turn the analogy around and use those ideas to solve your problem for the higher rank setting.
Oh, it's a good question. Yeah, I don't know. It's the short answer.
Okay.
Yeah. Wonderful question, though. Yeah.
Okay, so John, if you stop sharing your slides, maybe get set up with the channel. Okay, let me introduce the panelists. Really great to have Stephen Jordan here from who's at Google Quantum AI as a quantum algorithms researcher. Stephen got his PhD at MIT. He was at NIST and Microsoft, and then also did a couple of years stint at the White House Office of Science and Technology Policy. Stephen, he maintains the quantum algorithm zoo. He worked on the famous Jordan Lee Fresco paper giving quantum algorithms for quantum field theories. Towards towards justifying the quantum church-turing thesis. His recent work on DQI, decoded quantum interferometry, is really interesting. So, Stephen, looking forward to your take on what John spoke about. And then Robert Huang, who's starting as an assistant professor at Caltech and also a senior researcher at research scientist at Google Quantum AI. So Robert did his PhD with John Preskill and Thomas Wittig. And his dissertation was Learning in the Quantum Universe. So this is a really nice view of how you would work with quantum objects in a truly quantum, doing quantum learning. And of course, Robert introduced this technique of shadow tomography, which has been extremely influential. So Robert, welcome too. And so maybe we can get started with Stephen and Robert and with your reactions and thoughts about John's talk. Stephen?
Sure. Yeah. Well, yes, I remember when I first saw this work, to me, it came out of the blue. So that's kind of one reason I was excited about it. It wouldn't have occurred to me to ask this question about whether finding the hidden cut was possible. And if it had, my guess would have been that no, it can't be done in polynomial time. And even so, and then the other part was connecting it to Simon's problem just seemed so miraculous. And so I was quite excited by this. And yeah, then I think the other thing that struck me was that it seemed like a very natural primitive that sort of must have generalizations and applications. And I feel like we haven't found all of them yet. And that's the part that I find still very intriguing on a continuing basis. One of the things I always do anytime I learn something new, pretty much, is ask myself whether it can solve the graph isomorphism problem. And investigating that led me to ask one of the same questions, which was, I think, number 4 on your last slide, which is, to what degree can you solve this entanglement testing problem for mixed states? And I guess you said it was an unsolved problem, but one of the specific things I was wondering about was, whether there's at least something known about it as opposed to just, really completely open. But in general, I would say, yeah, things I'm quite curious about are sort of connections to more traditional hidden subgroup problems, and especially the fact that you could take something that sort of at first glance naively looked like it should be a highly non-abelian problem having to do with the symmetric group, but you're able to kind of finagle things so that it gets abelianized and turned into Simon's problem. And somehow that felt like a powerful trick that might be useful somewhere else. So maybe I'll turn it over to Robert.
Sorry, can I just intercede quickly, about this testing entanglement for mixed states? So why do we think that it's even plausible to do?
Oh, I guess it depends on what you mean plausible. So yeah, I can tell you the state of the art on this, which is if you have 2 systems that are d-dimensional each, then the overall mixed state is d² dimensional. So it's described by d² by d² matrix. One thing you can always do is just run full state tomography. It's going to take d to the 4th time. You learn the whole state, and then you run some sort of extremely inefficient algorithm to actually compute whether this thing is entangled or not. The lower bound that we have is just a d² lower bound, and it kind of follows by reduction from testing if you're a maximally mixed state. So maximally mixed states are not entangled, but you can find states that are somewhat close to them that are entangled, and distinguishing that takes d squared copies. Ultimately, I think it's going to be a computationally inefficient algorithm no matter what you do. But I think an algorithm that could improve on the d to the fourth trivial bound that you get from quantum state tomography might teach us just something interesting about entanglement that we didn't know before. For example, what we know about entanglement right now is just not sufficient to answer this question. So yeah, I think it's just an interesting kind of lens to probe the question of entanglement with, rather than maybe being something that you would implement in the lab and do something like that.
Yeah, great. Thanks. Robert?
Yeah, so it somehow like the result was so elegant and seems so fundamental that I would have thought that like 10 years ago or even longer, 20 years ago, people would already have come up with it. But in fact, this was not true. Like people thought maybe some of these problems was actually computation very hard, and this new link between state learning and hidden subgroup problem only arises very recently was I find it very interesting, and also like I feel like one of the principle or perhaps one of the ideas that was involved was like previously there's one could apply quantum union bound or quantum stress surge or more broadly speaking shadow tomography to create sample efficient methods for solving all kinds of learning problem, but in almost all of the cases they would become computationally inefficient. And it does seems like this technique that was laid out here would really help a broad family of them to become computationally efficient. So one of the question that I'm curious about was like right now it seems like it was very strictly focused on this hidden cut problem. But by just playing with the groups and playing with the hidden subgroup, there should potentially give rise to all kinds of other learning problems where this could arise, right? So right now, it sounds like Adam was saying after QIP, there were a bit more broadening of it. Like maybe now it seems like it also encompasses some of the questions from Bell sampling. Another question that came to my mind was when we were playing with shadow tomography, we were thinking about the problem of predicting all Pauli observables. And one of a specialized form of it was, suppose I have a mixed state, which is like I plus p over 2 to the n, where p is some Pauli string. And the goal is just to identify that unknown Pauli string. And it sounds like that might also become a form of this hidden subgroup problem, because like the way we solve it was also like having two copies and doing some Bell sampling and then solving like a Gaussian elimination, like a kind of a linear systems in over a finite field to reconstruct what the Pauli string is. So maybe that also is an example that could lie into it. But it just felt like there should be a really broad family of it. So I'm curious, like, yeah, right now, what is known and has this been broadened? To what degree? Are there other new tasks that emerges? Like maybe it would like you guys found this hidden cut problem that can be solved efficiently, and then the broader framework would also contain things people know that one could solve efficiently. But then maybe after that generalization, it can start covering new questions. I'm just curious, like at this stage, after a few months of putting it out and finishing this work, what is the current understanding?
Actually, Adam, you want to take this one? I feel like you've talked to more people than I have.
Sure. Yeah, I can yeah, so like I'll give you one example of some like generalization of this framework, and this, emerged from conversations with many folks at QIP, like Andrew Georgiou and Anand and Chinmay Nurki and various folks. So like here's one example. Let's say I give you a quantum state psi, And let's say that it's stabilized by, let's say it has a small stabilizer group, right? So it's not a stabilizer state, but it's a state that has a few stabilizers. Like, for example, let's imagine it has one Pauli stabilizer, right? And then let's imagine that all the other Paulis are very far from stabilizing the state. Given such a state psi, could you learn the Pauli that stabilizes it? Like, so to give you one example, like, well, if you took a Haar random state and you conditioned it on being the +1 eigenvalue of a random Pauli, right? Could you tell that there's a Pauli stabilizing the state, right? A Haar random state doesn't have any stabilizing Paulis, but if there's one hiding there, can you find it? And naively, that looks like an exponential search problem, but you can actually, as a consequence of some of these prior Bell sampling arguments, that you can actually learn that there's a Pauli stabilizing the state. Okay, so now one thing that I learned is like you can recast this as a state hidden subgroup problem, and there's an abelianization trick that lets you find the hidden subgroup very efficiently. So okay, so what's the idea? So if you have a state psi with a single stabilizer, this can naturally be phrased as a state hidden subgroup problem over the Pauli group, right? You have some parent group, which is the Pauli group. There's some subgroup H of the Pauli group such that H psi is equal to psi, right? And then and then let's say for all other Paulis, they're very far from stabilizing the state. Like they move the state far away. So this is naively, this very directly is like a state hidden subgroup problem over the Pauli group. Okay. But once again, you have this problem that the Pauli group is non-abelian. So this looks like a non-abelian form of a state HSP. So how can we possibly hope to solve a non-abelian state HSP? It looks like we're doomed. Okay, well, how do you solve this? Well, the way you solve it is like there's a slick abelianization trick where you say, well, instead of representing my Pauli P by P acting on psi, what if I represent my Pauli P by P tensor P acting on psi tensor psi? Well, now P tensor P deletes the phases from the Pauli group. So everything's abelian. So the Pauli group, if you mod out phases, is Z2 to the 2n. Right? It's just some really the X and Z's just act independently, right? So now you can via this representation define a state HSP over an abelianization of the Pauli group, right? And then now you can solve it efficiently by our framework, right? So you just now your group representation is P tensor P acting on psi tensor psi. You use 2 copies at a time. And from that, you can get, strings orthogonal to the subspace, and you can learn the subgroup of Paulis that stabilizes the state up to phase, right? And, afterwards, you can learn the phase if you want to with like a simple, simple test if it was a +1 or -1 eigenvalue. So this actually says that, you can efficiently learn if a state, say, has a single, if a state just has a single Pauli stabilizer, you can learn it by the state HSP framework too. But again, the key trick is always like take the non-abelian thing, that looks hopelessly complex, make an abelianized like representation of it or restrict to some abelian group, and then everything works efficiently in the abelian group. So I think that's the sense in which we've since realized some of these state HSP things can generalize some of these results that came out within the last few years in like stabilizer testing, stabilizer learning literature.
Actually, Adam, why wasn't this an answer to Maris's question about phases?
Yeah. So yeah, that's a great question. If with your representation, like if you know the phases are like a discrete root, like an nth root of unity, you can always take an n-fold copy of your representation and you can project out the phases if you wish to, right? Or
you could take the
take the trans. Yeah, our tensor R star.
Yeah,
and you'll delete the phase information. Yeah, great point. Yeah. Yeah.
I guess maybe to follow up Adam's answer, one more thing. It's like, when you take an intro quantum computing class, you see Shor's algorithm, and then they generalize it to HSP, and then it's really depressing because symmetric group doesn't work, dihedral group doesn't work, and then you're like, well, okay, I guess HSP doesn't work. And maybe one way of looking at our paper is that Well, people have been doing HSPs for a while in state learning, especially for stabilizer testing and learning and shadow tomography. And maybe it's nice to finally put a name to that and say, actually, no, HSPs, yeah, they're more broad than maybe they first appear.
And also like yeah, like in one of your slides, you also mentioned that like the state isomorphism problem where we try to test if two states are connected by just permutation. Could you elaborate on that? Like is it covered by HSP, and then that can be solved efficiently within this framework? And also if so, then on top of that, if I change the equivalence relation instead of just talking about permutation, but if I talk about also things like shallow circuits, which naturally comes from classifying phases of matter, or if I change to other things, do you feel like that could be efficiently solved?
Yeah, so this paper, it's like kind of cool actually. When you read back the way they define their problem, it's like literally exactly a state HSP problem over the symmetric group. But the bad news about the symmetric group, can't solve it. So they were actually putting forward this problem as an example of a potentially difficult computational problem. I would love to solve the HSP over the symmetric group, though.
I see.
But not hard information theoretically, I guess.
Yeah, easy. All of these things are easy information theoretically. Just Edinger, Hoyer, nil basically works here too.
In terms of hardness, do you have some ideas for how, like for example, you said this state isomorphism could be hard. You said rank 2 might be hard, or like instead of having actual zero entanglement across the gut, just a bit of entanglement across the gut. Like hardness kind of ideas. Do you feel like there are paths going forward for that, or it's kind of stuck right now?
Actually proving hardness.
Which I thought that was the original goal, right? Like you wanted to say that, oh, it's the random state can be generated just by like plugging them, or
Yeah.
one of the motivation.
I know for like this the state isomorphism problem. Okay, let me just say like a related problem is just the state HSP over the symmetric group, a more general problem. And you know, as I argued that like as a special case of that is just like the standard framework for solving HSPs over the symmetric group. That you could use to solve graph isomorphism, and people tried really hard to solve it. And eventually, so like these are Christopher Moore, Alexander Russell, Sean Holgren. Eventually, after not finding an algorithm, they just conjectured that that the HSP over the symmetric group is a hard problem. And using that, they were able to you know, build crypto systems based off of that. But my understanding is they were never able to, or they don't have anything like, maybe stronger evidence for it, rather than we tried, we couldn't get it. So we're going to conjecture it's hard. So that's kind of my first instinct, just to say like, well, one can conjecture it's hard, but I don't know how to give stronger evidence there. That's for the symmetric group one. I don't know. I haven't thought about it for the rank 2. Adam, do you have any?
Yeah, sure. So I guess yeah, it's a really great question if it's if it's cryptographically hard to learn like a rank 2 state across an unknown cut. There's a strong connection here between this problem and learning parodies with noise problem because I think maybe as John mentioned, like if you run our algorithm on a state with low entanglement across the ket, you get a variant of LPN out. Like you get noisy linear equations. Like you get random Ys where 90% of the Ys are orthogonal to your cut and 10% aren't. So solving this looks like a variant of LPN. So if you show that we're in the other direction or cryptographically hard, it would be really cool because it might say something like, oh, like what if this quantum problem is equivalent? It would then show something like this quantum problem is like equivalent to LPN or something like that, right? Like if you could show it's LPN hard, that would show, say this is a quantum equivalent definition, like learning a low entangled state. I think what we know, in terms of trying to prove hardness of this problem, I think we know that you can't get this low of entanglement in existing constructions of pseudo-random states or pseudo-entangled states. The reason is something like this. So like one way you can construct a pseudo-random state or with low entanglement is you take a binary phase state and then you apply a lossy function like a many-to-one function to the phases across the cut, and kind of the amount of loss you get, that is like the more many-to-one it is, you can show the lower the entanglement gets across this cut. The issue is that if you try to take those constructions to the point where they get constant amount of entanglement across the cut, this ends up meaning you'd want to have a lossy function where the collision probability is a constant, but of course such a lossy function can't exist, right? Because if you have that many collisions, you can just very easily learn it by just querying the function a few times. So I think the one thing we can concretely say is that you need a completely new pseudo-random state construction or pseudo-entangled state construction if you're going to try to hit this low of entanglement across a cut.
Yeah. Great. Any final thoughts? Or,
We have a couple more questions in the chat. Maurice is following up. If you can go the other way and take the usual hidden state problem for some bad group and turn it into a state hidden subgroup problem for a more favorable group with a worse orthogonality.
It'd be nice, but yeah, I don't know.
Yeah, that's a great question. I don't know. Yeah. Somehow, like, yeah, there are like multiple, things going into the algorithm. Like one is this abelianization of the problem Stephen mentioned. The other is you allow this non-orthogonality or approximateness of the representation. And so far most of our guys focused on the abelianization, but yeah, there's a great question whether this approximate orthogonality allowance buys you something. Yeah, I think the short answer is we don't know. Yeah, great question.
And then we have one other question about whether there's sort of a classical version where I replace the qubits with random variables. And instead of having them entangled, I'm just asking about correlations between the random variables.
Oh, so it's like I sample from two correlated distributions, a string of length n and another string of length n, and then I scramble the that gives me a string of length 2n, and then I scramble the bits.
That's how I understand the question, yeah.
Yeah, it's a great question. I don't think our thing solves it for the thing that I identified in the chat, which is that that's if you try to purify it to a sampling problem, you get entangled with some random seed registers, so it becomes the mixed state version of the problem that we don't know how to deal with. Yeah.
I'll yet another example.
It's also interesting, just a pure classical question. Like, has anyone studied this in the classical property testing literature? Like learning the productness of a classical distribution. So yeah, it's a great question.
Isn't the point that in the quantum case there's the swap test and there's just nothing imagined on the classical side?
Yeah.
I think people have studied this question of like, how do you tell if a distribution is independent or not? Like, I think I've seen papers on this, but I've never seen one where it's like you generate stuff and you scramble it up. Could be fun. Steven, you were going to say something?
Oh, yeah. It seems like maybe another manifestation of Q sampling being much more powerful than classical sampling. Of course, we've mostly been talking about algorithmic applications, but I also wondered whether this could have some applications either in quantum sensing or in some quantum complexity protocols, like something with Merlin and Arthur, and maybe Merlin's trying to fool Arthur by entangling things together, but Arthur can catch it now because he's got this protocol. I couldn't think of a concrete example, but it kind of felt like maybe there could be some application like that.
Yeah, I feel it's too fun of a problem not to have a cool application somewhere.
Mhm.
The one thing I'll say, and probably Adam can take over here, is that I think Adam and Tudor really want people to run this experimentally.
Yeah. The interesting thing is this algorithm is actually it's actually looks quite experimentally feasible. The reason is that, if you so you have to prepare two copies of your input state. Okay, so that would clearly be the hard part. But once you do this, your circuit is just like you Hadamard, do some C swaps, like some Fredkin gates, and then you Hadamard and measure, and it parallelizes like perfectly, it's on a 2D grid, like the qubits are lined up with like your control qubits and the two copies. It's a qubit by qubit operation. So it looks like something you could actually run on a near-term quantum device if you had a good, Fredkin gate fidelity.
Actually, so in terms of that, I guess the effectiveness, wouldn't it be related to the question if instead of product, you were trying to distinguish between, epsilon far versus delta far? And what's the complexity of that? Or how well does the algorithm work there?
Yeah.
I think it would work. Yeah, okay. It's a great question. It would probably work if epsilon is very small, but like some small inverse polynomial. But I think it's open if epsilon is like a small constant, if you could still get the algorithm to work.
Yeah, you're asking like
It's a great question.
the tolerant testing kind of the problem.
This is closely
The
related to
what?
what Dominic
Sorry.
was asking about tolerant testing. Exactly.
Yeah.
Yeah, I wouldn't be surprised if like, well, maybe it does this thing similar to what happens in the rank 2 case where like most of your samples are in H-perp, but like some of them aren't. What do you do there?
Yeah.
Exactly. Maybe the main experimental challenge would be like Simon's algorithm is just not very noise robust, and that you get these random strings. You really need them all to be orthogonal for the Gaussian elimination to work. If a few of them aren't, you're really in trouble. You're in LPN territory. So.
You're saying people should
But there's still like a finite size experiment question of like, well, how good would you need to get it so that there's at most one or two bad strings in your sample? I think there's a fine-grained question you could work about how big of an experiment you could actually run.
So when the state are, let's say, always slightly depolarized, like there's a constant global depolarized, like the same setting, but it's just now they're slightly depolarized globally in a very simple form, like white noise. Do you expect your algorithm to work? I guess you're saying that probably it wouldn't work, but
No, for the same reason Simon's algorithm shouldn't work there either. Like actually, this is something I give on one of my intro quantum like homework problems. It's like, well, if you have Simon's algorithm and you noise the outputs, like, oh, now can no longer solve it.
and also hardness is unclear. It could be that there's hardness. Like oftentimes when given a problem, when you white noise it a little bit, then suddenly you can just reduce it to LPN or LWE, and then this would become provably hard. Like this I plus P task that I said, where we know how to solve it in the strict case, when we put in like a white noise, like constant white noise, then suddenly we can prove that that's hard. So perhaps this locating unentanglement question might also have that feature, but maybe not. So.
I know that in the Bell sampling case, there's tolerant settings that you can get.
That is true, yeah. And actually they're fairly
this idea
close to each other, right? Like the completeness and soundness parameters that you can get.
I think the tolerant algorithm sort of uses some additional ideas.
Oh, but what I mean is like the completeness epsilon and the soundness delta that you allow for,
Right, yeah.
I think don't have too big of a gap.
Yeah.
And that allows for mixed states. It's not just like pure state tolerant testing. It's
No, I think it should allow for mixed states. So the idea is that you sort of like use the Bell samples to estimate Pauli expectation values, and then you sort of find the ones which are close to 1. That's how you do.
Great. I think we are running out of time here, but if there's any last thoughts? Otherwise, thanks, John, for a great talk, and thank you, Stephen and Robert, for lively discussion, and of course, also Adam and Dominique. So that was really fun. Thank you. See you next week.
Yeah. Thanks all.
Thank you so much.
Everybody.
Bye.
Thanks.